Some definitions we need to get a handle on. Multiprocessing. Multiprocessing implies multiple CPUs in a single computer. So this would be a motherboard that has sockets for 4 CPUs. Remember, a single core CPU can only handle a single thread at any one instant. So if I needed to improve the processing capability of a computer system, one thing I can do is add more CPUs. If I have multiple CPUs in a system, that system could be designed for either symmetric multiprocessing or asymmetric multiprocessing. This is generally defined by the capabilities or limitations of the operating system itself. In a symmetric multiprocessing system, the operating system, the kernel of the operating system, automatically load balances the work that each CPU is performing inside the system. It is mildly adjustable, very slightly adjustable. This is referred to as affinity. However, all in all, the kernel of the operating system manages the load balancing of all work on all CPUs, and it's at his discretion what CPU handles what processes. In asymmetric multiprocessing mode, the operating system supports the assignment of a single CPU for a single or collection of processes. In other words, I can dedicate a CPU to the operating system. I could dedicate a second CPU to my top secret processing of data, and then a third CPU might handle miscellaneous processing, so that I can now isolate the core operating system, some sensitive information, and protect that sensitive information from lesser secure information or processes. Here's an example of a system with actually 2 different systems with multiprocessors. In the left we see symmetric multiprocessing, where we have processor A and processor B, and the operating system automatically load balances those 2 CPUs, and there is little adjustability that we can implement from an administrative perspective. On the right we see asymmetric multiprocessing, where the operating system supports the ability to isolate processes or operating system or programs on 1 or more CPUs. More definitions that we have to look at here. The first definition we want to look at is called multi-threading. Now, this is where an application can manage processing of several instructions or threads at a single time. Remember, the CPU can really only ever work on a single thread at any one instant in time. So again, this is a 32-bit application. 16-bit applications only had 1 thread. A 32-bit application supports multiple threads. So we're implying here when we say multi-threading application that this is a 32-bit app and can support multiple threads, and the operating system can support those multiple threads. The next definition is called multitasking. Multitasking is where we can manage the processing of several programs at one time. And we say at one time. Only one of these programs / processes / threads can ever be worked on at any single point in time on a single CPU system. But because the clock rates are so high on these CPUs, it appears as though we are running 2 or 3 or 10 or 20 programs at the same time. Multiprocessing implies that there's more than one CPU in a system. That supports multiple threads. The more CPUs, the more threads. Recently, the development of the multi-core CPUs has become prevalent. So these rules we're describing here are for a single core CPU, can only process a single thread at a time. With a dual core CPU, we can now process 2 threads simultaneously. If we do have multiple processors in a single CPU, if we do have multiple processors in a computer system, we can implement either symmetric or asymmetric multiprocessing. The 4th definition we see on this screen is multi-programming. This implies the interleaved execution of multiple programs on the operating system. This is referred to as cooperative multitasking, which we're going to take a closer look at next. Here we're looking at the difference between cooperative multitasking versus preemptive multitasking. Back in the early Windows days, Windows for Workgroups specifically, they used a time-sharing process called cooperative multitasking. So actually the developer, the programmer who wrote his program, says when I get my turn in the CPU, when he starts paying me attention and working on my threads, I'm going to work this many threads and then I will cooperatively give up my turn. I will relinquish control of the CPU back to the operating system so that somebody else can take a turn. What this says is a couple of things. First, it's up to the courtesy, the generosity of the programmer, how often he gives up his turn. Once he gets his turn, he then can keep it for as long as he cares to. In other words, he could hog the CPU if he chose to. Now, where this caused problems is that because the CPU was waiting for the program to give up its turn cooperatively, if the program locked up or had some other problem where it couldn't reach the statement that says, okay, I give up my turn, the computer system now cannot process any other programs, processes, or threads. In other words, we've just killed the box and it requires a reboot. So back in the Windows 16-bit architecture days, the Windows 3X days, we used cooperative multitasking, and anytime a single app locked up, it locked up the entire CPU and we had to reboot the entire computer. That was unacceptable. So in the days of Windows 9X and Windows NT, the kernel of the operating system now takes control. This is referred to as preemptive multitasking. In other words, program, I don't care what you say when your turn is up. I'm in charge of this computer system and I'll tell you when your turn is up. So in preemptive multitasking, the kernel of the operating system declares when a single process's turn is up in the CPU, and he then controls the time slicing, the sharing of the CPU processor itself. So here are some examples. With cooperative multitasking, Joe's process is only done when Joe decides it's time for him to take a pause. And then he relinquishes his turn to Harry, for example. Harry then gets his time slice and he operates as long as he cares to until he decides to cooperatively give up his turn. He gives that turn up then to Fred, etc., etc. So it's all done cooperatively by the programmer themselves. They decide when they give up their turn. Now with preemptive multitasking, again, the operating system is in charge of when a particular process is done in the CPU, when that process's time slice has been completed. So the kernel remains in control of whose turn it is and when that turn is over. This is an example, this deadlock is an example of when a programmer hasn't written his code correctly. He's implemented or designed in a vulnerability. This is referred to again as the deadlock. This is where one thread or instruction needs a resource, and he can't move forward until he acquires that resource. But a second thread is consuming that resource and has it locked. So the first thread can't move forward because the second thread has that resource locked. The problem is that second thread can't move forward and release that resource until he acquires a resource which unfortunately the first thread has locked. So what we have here is a deadlock. The program has now crashed.